list unless someone just entered. Okay.
Professor, could you give me permission, please?
Sure. I'm sorry, I don't recognize who you are. What's your name?
Ricky?
Oh, Ricky, I missed you somehow. Okay.
Professor, I don't have it either.
Okay, hang on. Ricky, you have it.
Thank you.
And was that
Candace.
Candace? Missed you? Okay. Yep, you got it now.
Thank you.
Sure. Anyone else? Okay. So let me see if I can fire up OneNote. Okay. I can see it. I don't think you can yet. Let me see if I can share this with you. Maybe. Do you see what I see?
I can see it.
Yeah, it's kind of cut off, I think.
Okay, yeah, I'm trying to move it around a little bit. A little better?
Yeah, that's normal now.
Okay, good. So this is a reminder. So this was a slide from last week that we have our next exam, our second midterm on Friday, the 5th. So that's this week. It's the end of the week. And this is a reminder for me and for you that we're having a review session tomorrow. It looks like 4 to 6. Is that correct? I hope so. I think we agreed to that last week. And I didn't remember the other one. Okay, so we have 2 sessions. Yeah, one tomorrow and one on Wednesday. Is that right? Apparently. And that's fine. And well, yeah, so this one I'll be able to remind you of on Wednesday, or you could remind me. But today I'm reminding you of the session tomorrow at 4 to 6. So I'll send out a Zoom invitation for that. There was a sample test material. There's also homework and other things. So we should have room for this. About the test itself, so the normal starting time would be the starting time, the 10:30 starting time. Is there anyone who needs a slight adjustment on that, earlier or later? I'm okay with that. If you do, just let me know. Otherwise, I'll see you all on Friday at 10:45, actually. All right, so let me see what we also did the last time we were together. Let me see if I can just advance this page. So yeah, this was our most recent result. So what we did here was we considered a infinite birth-death chain, which is pictured here. And we tried to figure out its stationary distribution when it has one. And so we did this equation, pi equals pi p. That's the main equation for stationary distribution. And wrote that out, and it was, of course, an infinite number of equations, which makes it a little intimidating, but it turns out not to be as bad as it first looks. So when you first multiply this row vector times this column vector, you just get this boxed equation. That's because after the first 2 terms here, everything is 0, so you just get 2 terms. And then when you multiply this row vector by the second column vector, you get this equation. And in general, you've got an equation that looks like this box formula. So the 2 formulas for this are boxed. And I'm not going to go through it in great detail, but I'm just trying to go over it briefly, I guess. From here, we eliminated the return probability Rn because we know that in this scheme, let's see where it's at. Oh, it's up here. Qn plus Rn plus Pn is always equal to 1. Well, at least I should say almost always, except over here at the beginning where there's no Q. So in general, in this equation, you can eliminate the Rn by solving for it, which is what we did. And substituting that into this equation, it became this equation. And a term got canceled on both sides. And after a little more algebra, we were able to see that this expression was equal to this expression. And formally, they look the same. The only difference is here that you have terms in pi n and pi n minus 1. Here you have terms in pi n plus 1 and pi n. So they're offset by 1. Anyway, this holds for all n. And then if you play with the initial equation, which is up here, you can do the same thing, eliminate R0. And when you do that, you get this equation here. And long story short, what you get when you set these two equations equal to each other is a mechanism to solve for pi n plus 1 in terms of pi n. So it's really nice. You're trying to find all the pi n's, and it turns out that the nth plus 1 value is the nth value times this constant. So we wrote that down. And then we just used it, okay? So the first equation, this one here, gave us this. And the second, and all these gave us this. And so what we're coming out with is knowing all the pi's in terms of pi 0. So even though we have an infinite number of equations, we are able to solve for all the values in terms of pi 0 recursively. So for example, pi 2 is this, which we already knew from here. But then pi 1, we already knew this, so we substituted that in and got this. So everything, as you see here, is in terms of pi 0. And then we remembered that pi's are a distribution, which means they add up to 1, even though there's an infinite sum of them. So we wrote that all in terms of pi 0, factored out the pi 0, and this infinite series was left. And so one of the takeaways or the conclusions was that pi 0 was 1 over this infinite series. We called the series S for short. Be careful, don't mix it up with the state space. It's S for sum. And then if you solve for the other ones, pi 1 was S on the bottom, just times this on top. And in general, pi n was the same series on the bottom with this term as its numerator. Okay, so that's the proof. That's pretty much out of the book. Definitely should know the result. So the result is this. If you're on an infinite birth-death chain and you want to know the stationary distribution, you should have this memorized. This is the formula on the bottom, and then this is the numerator of it. Questions on the review? That's where it's coming from, and that's what it says. And then the next thing we did was a couple of applications, I believe. Yeah, so here was the first application. And in this case, probability is going upward 1/3 and down 1/2. And the infinite series looked like this, and it converged. And so we were able to actually figure out what the initial distribution looked like. It looked like all of this: 1/3, 2/9, 4/27, and so on. And this was, again, a different way to summarize what we know. A birth-death chain has a unique stationary different distribution if and only if this infinite series converges. Because if that series doesn't converge, then it goes off to infinity, then these things would look like 1 over infinity, which would be 0, and there'd be no stationary distribution at all. So you need this infinite series to converge for this to give you something meaningful. Here was an interesting second example, which is probably worth knowing as well, because this case, when P and Q were both 1/2, the infinite series actually diverged. And let me see. Well, this was trying to show this, but I think that the series diverges was easier than that, because the P's and Q's were the same. So these were all 1s, 1 + 1 + 1 + 1. So it clearly it diverges, which means what? There is no stationary distribution for this example, which I think I called like a coin flip, 50-50 chance of going up or down. There's no stationary distribution. That means there's no steady state distribution. And it also means that, well, since we already knew from a previous result that this was a recurrent chain, and since this doesn't have a stationary distribution, that meant these are no recurrent. So this would be our second example in class of a chain having a no recurrent state. Any state in here will be no recurrent. And that means even though the probability of returning is 1, it's a recurrent state, the average time it takes to return turns out to be infinity. And I was trying to show that down here, but I said the counting is complicated. So, but you could see that it looks like it might be going off to infinity, and it turns out it is. That's harder to show than it is to show that there's no stationary distribution. And if there's no stationary distribution, then that means, in this case, it means all the MIs are infinite. Okay. Questions on any of this stuff? Let me see if there was another, maybe after class I did a little more, perhaps. Not there, and not here. Okay. So I think I did an example of this again, where the P's and Q's were alternating. And I think that may have been an office hour. I don't seem to be having it immediately here. And it may also be in the sample test stuff I sent you. Let me just see if anything else is here. No, everything else is with regard to my other class appears. So I'm not quite sure where that is. Okay, so let me move on. Let's add a page, throw some lines on here, if we can. Okay. So since the test is Friday, this would be the last day that I'd add any material that I'd actually consider testing you on. I guess maybe just one more time say what we just said. So summarizing what we just went over. So for a birth-death chain, for an infinite birth-death chain, looking like this. So the probabilities going up are P's. And we're calling them P0, P1, P2, P3, etc. And the probabilities going down are the Q's. Q1, Q2, Q3, Q4, etc. And there could be return probabilities here, R1, R2, R3, so forth, and R0. So something looking like this has a unique stationary distribution pi, whose entries are pi 0, pi 1, pi 2, etc. If and only if and what was it? I think it's 1 plus pi 0 Q1, I believe. It's pi 1, pi 0. Q2, Q1. Pi 2, pi 1, pi 0. Q3, Q2, Q1. If and if only if this infinite series converges. Okay. And in that case, we know how to find the stationary distribution. I won't go over that again. I just did, but I'm just summarizing the result. So there's that. And if it then there's another if and only if. This all happens if and only if all the states are what? Positive recurrent. So if you're given a birth-death chain and you're asked to prove or show that all the states are positive recurrent, it's equivalent to looking at this infinite series and convincing yourself it converges. And since the P's and the Q's can be a variety of things, you should go back and look at infinite series from your calculus class. And I talked about that a little bit. In fact, I said common infinite series that you should go back and look at would be the geometric series, because you know when they converge, hopefully. Telescoping series, common Taylor series, things like e to the x and sine and cosine and maybe log. Those are other examples, and P series. So those are all calculus kinds of series that you had, and you should review to know when they converge and when they don't. Because if you have an infinite series that comes from a birth-death chain like this, and you want to know if the states are positive recurrent, the easiest way is to recognize whether this series converges or not, because then you have all this material from calculus that you can use. Okay. Now, the other result that we pulled this with, which came from chapter 1, was back on page in equation 68. So if I fish that out and put it next to this, just to make a nice pair. Yeah, so we have this result from page 33. So we also know that the states are recurrent if and only if. We also know that the states are recurrent if and only if and it's on page 33 if you want to see it. If and only if this series, the one that looks like 1 plus Q1 over P1 plus Q2 Q1 over P2 P1 if this one is infinity. Okay. So we did that before. That's in chapter 1, as I said. And I put it down because it's good to know. And also they're a little confusing. Slightly. How are they confusing? Well, this one has the P's on the top. This one has the Q's on the top. So you don't want to mix them up. Moreover, these line up sort of perfectly. The Q's, that the appropriate indices are right there on the bottom. So Q2, P2, Q3, P3. These are offset a bit. P1, P0, and on the bottom Q2, Q1. So I'd say this would be a little harder to remember than this one. And if you have both these results in your mind, which you should when Friday comes rolling down, then you'd be able to answer questions like, when do you have a positive recurrent states? Well, that's this one over here. If this converges, then the states are positive recurrent. But suppose this series diverges and this one also diverges. The fact that this one diverges means all the states are recurrent, but the fact that this one diverges would tell you that the states are not positive recurrent, but they are recurrent, so that means they would be null recurrent. So if you have an infinity here and an infinity here, for both of these series, then you're talking about no recurrent states. And those are sort of elusive, hard to find examples, but that would be some criteria or condition in order to find that. Questions on any of that? So coming into the test on Friday, oh, by the way, with regard to the test, I am in the middle of grading them. And the scores look decent. If I had to generalize it, okay. Now it's hard to say until I grade them all, but I was happy so far to see that the scores are looking pretty good. Hopefully I'll have it for you Wednesday. But what I was saying for the test on Friday, this one is certainly something you should know because it's in chapter 2 and we just showed it. And also you should know the stationary distribution, which I could ask you, which has this series on the bottom, and then it just picks off the relevant terms of this one, and those become the numerator. So you should also know the stationary distribution from this result. But I think you should still remember this, even though it's from chapter 1, because it sort of pairs with this. This shows you when a birth-death chain is recurrent or not. this tells you when it's sort of positive recurrent or not. Okay. What else do I want to talk about today? Well, let me scroll down a little further if I can. I'm not sure I can. It's stuck. Let me see if I can get it unstuck. I'll just go to another page and come back. And that's not working. Okay. Well, it doesn't matter. I'll flip the page then. Well, one thing we'd like to settle, and haven't talked about it lately, is the difference between stationary and steady state. So remember, pi is a stationary distribution. What does that mean for us? It means that, well, for distribution means all the entries add up to 1, but that's not the hard part. The hard part, or the part you need to remember, is that if you take this vector and you multiply it by its one-step transition matrix on the left, you get back the same vector. Okay, so that's what it means to be stationary. And we've done stuff with this. We've figured things out by hand. If there were 2 or 3 states, we've done that by hand. If it's more than 3 states, you still can do it by hand if you wish. And actually, the proof I just went through for the birth-death was sort of by hand. It had an infinite number of states, in fact. But more commonly, if you have something like 4, 5, 6, 7 states, the way that we would be expected to do it, say on the test on Friday, would be using the algorithm that we talked about in class. I don't want to go over that at this moment, but I do want to refer to it. That's a way to solve for the system. So we can summarize this and we can find pi, I suppose, in 3 different ways. In 3 different ways. What are the 3 different ways? By hand. And if you do it by hand, remember, in addition to these equations, you also have the fact that it's a distribution, which means the entries sum up to 1. Without that, you'll be in trouble. But you can do it by hand, and we've done so. And there'll be something like that on the upcoming test. But you could also do it by the algorithm. And then the third is by formula. So we just came up with a formula for the birth-death chain, just referred to it. So we can make use of that already known formula. So here are 3 different ways you can find the stationary distribution. Okay. Also recall pi is a steady state distribution. Well, which means and we had 2 ways to think of what it means. One way was the following. So definition, it doesn't matter what you call it, definition 1 or 2. Definition 1 would be the limit as n goes to infinity of the n-step transition probabilities, say from I to j, that these guys approach pi j. Something that just depends on the state you're going to as n gets large. So this limit would have to hold for every I and j in state space. So one way to think of that, and I guess I should say where the sum of these guys. So let me just write in this summation. I, for all the states I in the state space should add up to 1. So so it's harder to be a steady state distribution. Why? Because it's a limit. And limits are harder than solving some algebraic equation generally. So this is saying that the n-step transition probabilities approach a distribution which really just depends upon the state you're going to, not upon where you started. This was one definition. Our second definition, definition number 2, was different. It just said the limit as n goes to infinity of the probability of a time n being at a certain state equal pi j, and this limit equal that, again, where the sum of the pi's equal 1. So this is saying that as n gets large, the probability that the Markov chain is at a particular state is getting close to a constant probability. And this happens regardless of where we start. So it doesn't matter where you are at time 0. As n gets large, the chance that you're at state j approaches a limit. And it turns out these are equivalent. Now they're both limits, so that's not too surprising. So this one says you can think of the entries of the n-step transition matrix as getting close to these constants. And this says you can think of the probability at time n that you're at a certain place is getting close to this. And either one we call steady state, because what we're really saying is as n gets large, the system is showing some regularity. There's it's not just going off in unpredictable directions. The limits actually exist. Now, it turns out the main result between these two, in most applications, people want steady state. This is the stronger result. So it turns out if pi is a steady state distribution, then pi is a stationary distribution. I'll just abbreviate that distribution each time. So, okay, once again, it doesn't let me scroll. I wonder what's going on here. Well, so I'm just going to cram something in here since I don't have much room. If you know pi is a stationary distribution, it may also be a steady state distribution, but it doesn't have to be. On the other hand, if you know that pi is a steady state distribution, then it has to be stationary. And the easiest way to see that, I suppose, let's see the easiest way to see that. Probably would be this, that if you look at the distribution at time n, there's this relationship between it, which we had back in the other chapter. I have to be careful here though, because the notation is a little different. So here's something we had in a previous chapter, chapter 1, that if this is the distribution of this Markov chain at time n, then the distribution at time n plus 1 is equal to this. Okay, and these are both vectors. So this is something we knew in chapter 1. Now, if the steady state distribution exists, that means this thing has a limit. So as you take the limit as n goes to infinity, both of these will turn into this. So if you know the limit of these guys approach, which is what this thing is saying here, the steady state limit exists, take the limit of both sides, you get this, which is the definition of stationarity. So the limit result is stronger than the algebraic result, okay? So in terms of the picture, steady state is usually what we want. And usually how we find it is to find if there's a unique stationary distribution, and then show that that stationary distribution is also the steady state. Well, let me flip the page because there's a theorem that says exactly that, and that's the new thing I have to say today. So let me flip the page. Throw some lines on it again. I can't see the lines. I don't know if I got them or not. Now I can see them. Okay, so in the book, there's a theorem that's worth talking about. I'm not going to prove it, but it's worth referring to. It's toward the end of the chapter. It's theorem 7 on page 73. So take a check out your book. Page 73, theorem 7. And here's what it says. So it says, let Xn be an irreducible positive recurrent Markov chain having stationary distribution pi. So suppose Xn, so here's our Markov chain. We can think of it as just as where you are at time 0, 1, 2, 3, etc. Is a Markov chain, is an irreducible Markov chain. Having, well, let's be careful, is an irreducible positive recurrent Markov chain having the unique stationary distribution pi. And if you ask me, how do you know it has a unique stationary distribution? Well, that's theorem 5. Theorem 5 says, and we didn't prove it, but we have used it a number of times, says if you have a irreducible positive recurrent Markov chain, then it has a unique stationary distribution. And it even tells you more. It tells you what? It tells you that the probability at any point, any state I is 1 over mi, right? Where mi is what? Expected time it takes you to go from I back to itself. So that's all, that's theorem 5. And we're assuming that the hypothesis of theorem 5 that we have a Markov chain that's irreducible. So every state goes to every other, leads to every other state and so forth. And that they're positive recurrent. Then it has a unique stationary distribution pi. And we're assuming all that. And then they add this. If the chain is aperiodic, if the Markov chain is also aperiodic, and before you ask me what that means, then I'm going to tell you what that means in a moment, so just sit tight. But if you have this condition, which is called aperiodicity, then what happens? Then the limit exists. As n gets large, if you look at the n step transition probability from I to j, then it equals pi j. Which says, or which means, pi is also the steady state distribution. Now, why do I say the steady state? Well, if there's a steady state, there's only one. Limits are unique. If they exist, there's only one. So saying that the limit of this expression is equal to this, well, back on the previous slide, this was one of our definitions. This was the first definition I gave of what it means to be a steady state distribution, right? The entries in the n-step transition matrix as n gets large approach constant. That only depends upon where you're going, not where you came from. Okay, so this is an important theorem because it tells you that if you already have a unique stationary distribution, which you do by theorem 5, that is, if you have an irreducible positive recurrent Markov chain, such as the birth-death one we just talked about, then that will be the steady state, provided you have this condition, which is called aperiodic. So now that's the new idea. What does it mean to be aperiodic? So let me just tell you, because we're not, as I say, I'm not going to prove this anyway, I'm just going to use it. The period of a state is given on page 72. So on page 72, the period of a state in the Markov chain so here's a definition. On page 72 occurs the following definition. Let's suppose I is the state of the Markov chain. So I'm changing it slightly just to be I and J. Suppose I is in the state space of a Markov chain. And also assume period. Assume that the probability of going from I back to I n times assume that that probability is positive for some n or some n greater than 1. Let's make sure I got this right. Yeah, then we define the period of I to be d sub I, where d sub I is the greatest common divisor of all the n greater than or equal to 1, such that you can go from I back to itself with positive probability. Okay, so that's the definition. Let me see. Yeah, it's not letting me do much here. Let me see if I can fake this into letting me doing something. Write a little more. Yeah, that actually worked. Okay. So that's a pleasant surprise. Okay, so let me give you an example. Suppose you have a two-state situation. And okay, that's a rather simple two-state Markov chain. Let's figure out D0. So D0 would be the greatest common divisor of all n's greater than or equal to 1, such that what? Pn 0 to 0 is greater than 0. Okay, so what's in here? Is 1 in there? Well, if 1 is in there, then that would say that P1 0 0 would be bigger than 0. So can you go from 0 back to itself in one step? And the answer is no, because there's no loop. So So 1 is not in this set because this condition is not true. The probability of going from 0 back to 0 in one step is not positive. So 1 is not in here. What about 2? Well, yeah. You can go from 0 back to 0 in 2 steps, positive probability, because you can go away and then come back in 2 steps. And so you would have gone from 0 back to 0 in 2 steps. So 2 is in here. Okay. Is 3 in there? So what am I asking? Well, is this definition true? Can you get from 0 back to 0 with a positive probability in 3 steps? And the answer is yeah, because you can go over here, you can loop once, and then come back. And the probability of that path would be 1 times a half, which is positive. So that means 3 is in here. What about 4? No problem. You can go away, loop twice, and then come back. Okay, now it looks like everything else beside 1 is in here. So what's the greatest common divisor of all of these numbers? Well, you're looking for a whole number that divides them all. There's only one whole number that divides 2 and 3 evenly, and that's the number 1. So this thing has period 1. D0 is 1. D0 is equal to 1. In words, we would say the period of 0 is 1. Okay. Let's go on to D1. D1 would be defined in a similar way. It's the greatest common divisor of all the positive values 1 onward, such that what? Such the chance of going from 1 to 1 is positive. So if we want to find the period of this state 1, you just replace 0 up here by 1. Fine. Let's go through it. Is 1 in here? Can you go from 1 back to itself in 1 step? Sure, because you can loop. So this time, the GCD of something, we've got 1 in there. Is 2 in there? Sure. You can go away and then come back, right? Well, as far as that goes, you can just loop twice, right? So 2 is in here. Now, we can figure out all the things in here, but it almost doesn't matter because we're going to take the greatest common divisor of all the numbers in here. And the greatest common divisor of the 2 numbers we already have is just 1. So you're not going to get any smaller than that. So what do we have? So D1 is equal to 1 as well. Okay.
Professor,
Yeah.
in this case, we're not worried about the first time we get to a state, just how many times we get there.
That's correct, because we didn't put in capital T, which worries about the first time, right? We just put in the probability going from a state to another, to itself in this case. But you're
Thank you.
right. Yeah, no first time worries here. Okay. Now notice something. They both have the same period. That's not a coincidence. It turns out that if 2 states communicate with each other, then they each have the same period. That's a result. I don't want to take the time to prove it, but it's true. Let me see if I can push my luck a little further here and have this thing scroll down even further. I know I'm asking a lot. Okay, it's not letting me go further. I'm going to play with it another second, see if it does. Yeah, okay. This wasn't doing the right thing. I don't know what. Let's do another example. Example 2. So this is example one. We figured out the period. The period of this in this case is 1. Okay, example 2. So suppose we have something like this. Okay, so that's not much different than the other one. I suppose you can consider this a baby birth death chain, right? You're having only 3 states. Let's figure out D0. D0 is the greatest common divisor of all the n greater than or equal to 1, such that the probability of going back from 0 to itself is positive. Okay, so let's start with n equal 1. Can you go from 0 back to itself in 1 step? No. There's no way to do that. So the first number in here would not be 1. What about 2 steps? Sure. You can go up and go back. So 2 would be in there because you can go from 0 to 0 in 2 steps. What about 3? No, I don't see a way to go from 0 back to itself in 3 steps. Do you? You can see there aren't any. So 3 is not in there. What about 4? Well, sure, up, down, that would do it. And as already pointed out, it doesn't talk about going back for the first time, just it wants to get back. So since you can go up, down, and that has positive probability, it would be 1 times a half times 1 times a half. So 4 is in here. What about 5? Can you go from 0 back to itself in 5 steps? No. Now you might have to think about it a little bit. What's sort of killing you here is that there's not a loop in which would help you get back onto the odd number of ways of doing it, right? But there is no loop, so I don't see doing it in 5. And 6 you can certainly do because you can go up, down, and you got back there with positive probability. And I'm saying this continues. So what's the greatest common divisor of this guy? Well, the greatest common divisor of this would just be 2. 2 goes into all of them. Of course, so does 1, but we want the greatest common divisor, and 2 is bigger than 1, so that's why it's 2. So D0 is 2. Now, what did I just tell you from the previous example? I told you that if the states all communicate with each other, then they all have the same period. So let's just test it for 1, maybe. So how would D1 look like? D1 would be find the greatest common divisor of all n positive, where n is where you're going from where 1 to 1. So you're looking at all ways of going from 1 back to 1 in n times. And so can I fool this again? Let me scroll. I don't know. Yeah, okay. So let's figure it out. Can you go back? Can you go from 1 to 1 in 1 step? No way. There's no loop. There's no way. Everywhere else you go away and have to come back. So the first time you could do it would be 2 again. Can you do it in 3? No way. Parity is wrong, right? You need an even number of steps to go away and come back because there's no loops again. So pushing us along a little bit, this is going to be the same thing. And the GCD of this is now 2 again. And if you wanted to, you can check for yourself that this is also 2. So each state in here has period 2. Each state in the previous example had period 1. If you have period 1, it's called aperiodic. If you have a period bigger than 1, such as 2, 3, whatever, then it's called periodic. So now we can go back to this theorem. If the Markov chain is aperiodic, it's already irreducible, so we know that all the states have the same period by the previous result. But if they're aperiodic, that means the period of all of them is 1. Then it turns out the stationary distribution that you had is also the steady state. So what's going on is this thing won't reach a steady state, but this one will. Now let's just do that real quick if we can. Oh goodness. Let's look at the P matrix here. The P matrix here is you have to go up. So going from 0 to 0 is not possible, but you have to go up and you can't go to here. And from here, you either go down, which is 1/2, or you stay. It can't go back to itself in one step, but you can go up. And what about from 2? Well, from 2, you can't get to 0 in one step, but you can go down, and it's like this. Okay, so what I'd like you to do is take powers of this thing. Maybe you can do it on your calculator because I don't have one right at my hand's reach. What does P squared look like? What does P cubed look like? What does P to the 4th look like? Can someone help me with those? I'm being a little lazy, but I'm hoping someone will come up with them. Anyone got P squared? Okay, I'm going to race you, but I'm hoping you beat me. Because it would be sad if I can find this faster than you.
I have it, Professor.
Okay, what do you got?
D squared is 1/2, 0, 1/2. Then 0, 1, 0. And then 1/2, 0, 1/2.
Great. Can I get greedy? You got the next one?
It's just the original. It's just the original matrix.
Perfect. And then this would be P2, right?
Yeah, and then it just keeps repeating.
Okay, so thank you very much. And let's look at what's going on. So this is P1, this is P2, this is P3, P4 would be back to P2. This keeps erasing, but it's no matter. Let's just look at the upper left-hand entry. P11, so that's the probability of going from 0, 0 rather. In one step is 0. And the chance of doing that in 2 steps is 1/2. And the chance of going from 0 to 0 in 3 steps is again 0. And the chance of going from 0 to 0, this is 1 step, this was 2 steps, this was 3 steps, this is 4 steps. And that's just going to be 1/2 again. So I'm looking at the probability of going, I'm just looking at I'm just looking at these entries. I didn't even write before, but it's back to half, okay. And if you look at the limit of these things, 0, 1/2, 0, 1/2, 0, 1/2, that's an infinite series. But it has no limit, right? Because if it had a limit, it would be getting close to 1 and 1 number only. And it's not, it's oscillating between 0 and 1/2. So what does it say? It says this thing here doesn't have a steady state. Why? Because if it had a steady state, our definition of steady state, which I think is no longer on this slide, unfortunately. Yeah, it is. Okay, it's there. Well, sort of. This is the definition. The definition of steady state would be that these transition probabilities are getting close to 1 number. And it only depends on J, not where you start, okay? But this limit doesn't exist. It's pretty clear in this case that 0, 1/2, 0, 1/2, 0, 1/2 doesn't get close to 1 number. It keeps bouncing back between 0 and 1/2. So there's no steady state, even though there's a unique stationary. How do we know that? It's irreducible. Positive recurrent, because it's finite. There's only positive recurrent states in a finite situation. So this thing does have a unique stationary distribution, looking like 1 over mi. I don't know, but yeah, this thing. But it's not steady state, okay? So what the theorem is saying is, you got to avoid guys like this if you're trying to get a steady state, because it has a period where it comes back every other time, but that messes up the limit. So when does the stationary become the steady state? When the whole thing is aperiodic, when there is no period. And by the way, there's a little going on here, and I'm running short on time, but you can see what's going on. If you have a loop, it's always going to become, the whole chain will become aperiodic. So any chain, so like this is the birth-death chain. So here's a birth-death chain that doesn't have a steady state. And why? Because it's pretty clear the limit of the sequence doesn't go anywhere. It oscillates. So it doesn't have a steady state. So after a long period of time, you can't tell me the chance you're at 0. Why? Because it's either 0 or 1/2, depending whether you're even or odd, right? That's the truth of the matter. It doesn't get close to 1 probability, it oscillates. So here's an example, a simple example of something that has a stationary but not a steady state. And yet, if you wanted to make it have a steady state, all you need to do somewhere is put in a loop, because that gives you an extra way where you can get off of this even odd cycle. And so I'll leave it to you. Why don't we make that homework? Why don't we change this? Well, I can't just put it in a loop without changing things. Where should we put in the loop? How about here? So we'll change it. So this is 1/3. And if that's 1/3, then I better make each of these a third, so it adds up to 1, right? Okay, so I've sort of taken the original example 2, and I changed the halves to a third, and I put a loop in at 1. Homework. Verify that it's aperiodic, which means what? Its period is no longer 2. Its period is 1. If it's aperiodic, what does the theorem say? It says you have a steady state. So the condition you need to make sure that a stationary distribution also is a steady state distribution is aperiodicity. It's a fancy word when you say it that way, but it just means it's aperiodic, or if you like, its period is 1. Not proving anything, just trying to explain it. Does it make some sense? Okay, well, let me give you a couple of other homework so that you can go for some of this. So this is the last homework that might be related on the test. We'll see how this homework goes. So homework, and I'll do some of it now if you want, or they start you out. Number 15 is sort of not really dealing with what I'm talking about here exactly, but it's close. More on target. $14, I guess. But I would change 14 to, it's 14 is something like we've done before. It says show it has a unique stationary distribution and find it. I would say show it has a steady state distribution. And I don't have to say unique steady state distribution, because if it has a steady state distribution, it's already unique because it's a limit. Limits are unique. Okay, so 14 and 15. $22 and $23, and that would be it. But on 22 and 23, decide if there exists steady state distribution. Okay, so 14, 15, 22, 23. Okay. Final reminder for myself as well as you, tomorrow when? 4 to 6, right? Is that right? What am I referring to? The problem session, right?
Yes, that's correct.
Okay, so I'm reminding you and myself at the same time. And if somebody wants to shoot me an email, you're welcome to, but I think I'll remember, but it doesn't hurt. It doesn't hurt to remind me. Very good. I'll take a little water break right now, and then we're sort of covered everything I want to cover in chapter 2. So this is breaking nicely. Next time I'll give you some things, a review for the test, obviously. And then we go into chapter 3. Okay, so I'll see you in about 20 seconds here. Boy, that water tasted good today. I'm gonna try a little more. Okay, so I'm back, ready to do the office hour. I would say relevant to today, the ones that are most relevant for today would be 14, 22, or 23. I'd say 15 is something maybe to do after you do these 3. Okay. So does anyone have any interest in talking, or well, I'll go with your request, whatever it is, probably, but I assume maybe one of these problems would make sense to do because it's connected to what I was just talking about. But you may have some other requests you have as well. So the request line is open. What do you want to see? Oh, excuse me one second.
Sorry about it.
Yeah.
Do I need anything to get the car swapped? Like I think I need the registration thing, right?
Your car,
Yeah,
it's in the glove compartment.
Oh, you already put it in?
Yeah.
there? Is it the new one that
Yep.
says you need? Okay,
Says all you need is a smog check.
cool.
And if you go to my guy, you can just go to.
Yeah,
triple-
I'm gonna go do it.
No,
Cause I
you-
have to run by the post office.
You going to my guy or someone else?
The dude that's by like Allen Tire.
Yeah.
Yeah.
Yeah,
That's the
just
only one
take-
I know.
Just take that and go to AAA and they'll give you the tags.
Okay, cool.
Sure.
Thank you.
Registering the car. Okay. So request, what do you guys want to see? Or any questions about what I said today? Because I've got the slides here, I can go over. It was sort of an easy day in the sense I didn't prove much, I just explained things. Yeah, Millie, you got something?
I was gonna suggest maybe 14.
I'm sorry, you're requesting 14? I think that's what I heard.
Yeah,
Got it.
number 14.
Okay, sure. So anyone else have anything else? Right now, I've got one request for 14. You know what? I'll pick 22 and 23, just, or one of them. So why don't we do 14? And then if you have a choice of between 22 and 23, let me know, but we'll do 14 first. So let's flip the page. Okay, and throw some lines on as usual. Good. And move all these toolbars out of my way. Okay, so let's look at 14. Okay, so 14 reads, consider a Markov chain on the non-negative integers having transition probability from x to x plus 1 being p, and from x to 0 being 1 minus p, where p is between 0 and 1. Show that this chain has a unique stationary distribution and find it. And I changed it to be show that it has a unique steady state one. Okay, so but all I have to do here on this is remind you we've already done this problem before. So let me do the diagram. So the chance of going up is always, what was it, P? If you're on, it's like a birth, where you're just having, one more individual than you had before. And then the chance of crashing, that was the chance that you went from X to 0 is 1 minus P. So that's this. 1 minus P. 1 minus P. One minus P. One minus P, and it keeps going. And there's a 1 minus P on this guy too, right? Okay, so now that I draw this, I hope you recognize it as something we did in class. It's a birth disaster chain. Disaster. Sure, I can spell disaster today. So I'll spell a harder word. Catastrophe. Birth catastrophe or birth disaster chain, either way. Okay. Now, we could do that all again, but I think it's easier just to find it. Let me just see if I can locate it.
Yeah, I recognize it. I think I just get a little lost in the notation sometimes.
Yeah, no, it's all
They
fine.
have it in P's and X's.
Yeah, yeah. Well, I've changed them here or there. Oh, here it is, birth catastrophe. So here's an example, and there it is. But let's see, I think we did more. I know we did more. Let me just see if I can find it. Oh, that's a different class. Oh, goodness. Let me just see. I must have done it, but more up here. Pardon me. Okay, here's another, there it is. Okay. So I'd like to have the answer here if I do. I don't think I was doing the stationary here yet. So I think at this point, I was just introducing the thing. And then I had two examples where all this, and this was problem 18 in the first chapter. And we're actually trying to show there that it was recurrent. Okay, so we did all that. Let me see if I can see where we went next. Isn't there? Oh, that's the algorithm. Something else. That's a different class. Here we are again. That was Wallace's stuff. That's a different class. Oh, goodness. I'm back into birth, death. Well, I'm trying to see whether I want to do it again or not. Hang on a sec. I'm not finding it, unfortunately. So let me go back to where I was. Where was I? Right here. Millie, do you still have it? I think it was.
Yeah, I'm sure I could find it in my notes.
Yeah,
I
okay.
didn't realize it was like that similar,
Yeah, so,
but it's okay.
well, yeah, but I sort of, okay, I'm trying to, let me throw this out to anyone, Millie or anyone else. If you can give me what pi was without having to redo it, that would be cool. Yeah, let me leave that out there.
See if I can find it.
Yeah, Millie, look, and if someone else could look. We did it. We found the stationary distribution. It was one of the first examples where we had, I think we did it in general. So I think I had P0, P1, P2. While you're doing that,
I think that, Professor.
oh, you got it?
Sorry. I think so.
Terrific. What is it?
I think pi 1 is just p times 1 minus pi, and then pi 2 is p squared minus 1.
Pi 1 is P times 1 minus P.
P, yeah, sorry, I'm sorry, it's pi, yeah, p. I don't know, I'm confusing my letters.
And this was like this.
Yeah, and it just keeps going.
Was there a P0 though?
P0 is 1 minus p.
Oh, I got it. Or pi 0, sorry. It's 1 minus P. It's hard when you have P. Pi and P are like the same
Yeah,
letter.
I think we get that pi of n is p to the n times 1 minus p. I
Okay.
just saw it just now too.
I know we did it, and I'm just trying to avoid doing it again. Okay, so this is, thank you both. 1 minus P is what you're telling me, and N could be 0, 1, 2, etc., right? When it's 0, it becomes this. Yeah, this is a geometric series. Okay, so since we did it before, and a couple people at least have it in their notes, I won't do it again. But this is the stationary distribution. That's what we figured out. And I'm trying to say, can we conclude that this is also the steady state? And in order to do so, what do we need? We need these states to be aperiodic. And the key to it is there's a loop. Whenever there's a loop on an irreducible chain, pardon me, from what we were just saying in class, it's automatically going to be aperiodic. Let me show you why. What would be the period of 0? It would be the, it's the GCD, greatest common divisor of all the n 1 or bigger, such that the probability of going from 0 back to 0 is positive, right? So we look at all the n that make that inequality hold. Okay. If you're at 0, can you get back in 1 step? Sure. It has a loop. So what's in here is 1. Pardon me. We don't have to go any further. Why not? Whatever integers there are beside 1, and I could already see there's 2, right? And I can also see 3 is in there. But it hardly matters what more is in there, because the greatest common divisor of these would have to be 1. Because 1 itself is there, it's a loop. So this is 1. You can't have an integer that divides 1 other than 1. Okay, so the greatest common divisor of all, even without knowing what else there was in there, doesn't much matter, because the greatest common divisor of this list has to be 1, because 1 is on the list to begin with. That's why the loop assures you aperiodicity. Okay, so that means D0 is 1. But what did I say in class? If it's irreducible, that means all the others have the same period of 1. And by theorem 7, that means the stationary distribution is the steady state. So this same distribution that I had you found in your notes that we did before is not only the stationary distribution, we can conclude more, it's actually the steady state. Now, what good is that? Well, that means if you wanted to say what's the limit as n gets large of the chance of going from one state to another, it's just going to be pi j. And pi j in this case will be what? P to the j 1 minus p. So the long-term probability of being at any state in this picture is known by theorem 7. And so this theorem 7 is just a small additional step to what we already did before. The hard part was finding the stationary distribution. That's the part I was trying to avoid redoing, but we did do that. And once you get it, then you have to give a little more of an argument to say that why this is the steady state. And the argument you need is that the states are aperiodic, which means their period are 1. And it's clear whenever you have a loop from what I just said. So this would also be the steady state distribution. That's all I wanted you to do for number 14. Does that make sense?
Yeah, can you repeat the last part?
Sure.
Yeah.
So in order to show something as a steady state distribution, Usually, you're going to have to find the unique stationary distribution that's guaranteed by theorem 5. In this case, I already did it before in class. I just can't put my fingers on where I did it, but I know I did it. It was solving an infinite number of equations in a birth catastrophe chain. And this came out as the answer, which you found and others found as well. So once you have a stationary distribution, that doesn't mean it's a steady state distribution, because the way it works is every steady state distribution is a stationary distribution, but not every stationary distribution is a steady state distribution. So to be a steady state distribution, you have to be a stationary distribution and more. What more? You have to be aperiodic. That's theorem 7. So the new part of the analysis was looking and seeing what the period of 0 is. The period of 0 is 1 because it has a loop, and that's enough to make it 1. That's enough to make 0 aperiodic. That makes the whole chain aperiodic. And you already have the stationary. That means the theorem tells you that the stationary distribution is actually the steady state distribution as well. But we're using theorem 7. My cold is beginning to act like a cold. Millie, were you okay with that?
Yes, that makes sense.
Okay. Why don't we double down and do one of the other 2 problems that I was suggesting? So let me see. Can I fold this thing into letting me scroll down? Oh, geez, like pulling teeth. There it goes. I really don't know why this works. Okay, so let's look at some of those problems. Any preference, 22 or 23? I mean, 22 is simpler looking. I don't know whether that means you want me to do the harder one, or if anyone has a preference, this is your chance. Otherwise, I'll pick the easier one. Oh, let's pick 22. I think they're similar. I don't think it's a big deal, to be honest. 22. What does it give you? Consider the Markov chain on 0, 1, and 2 having the transition matrix given as this. Okay, so they give you that. And this is 0, 0, 1, first row. 1, 0, 0, second row. A half, 0. Okay, just out of habit, I think I would do the diagram. From 0, you can't go to 0 or to 1, but you can go to 2. And the probability of going there is 1. From 1, you can go to 0. Probability 1, and that's all you can do. And from 2, you can go to 0 or 1 or 1. The probability of going here is a half. And the probability of going here is a half. Okay, so there's the diagram that goes with this one-step transition matrix. Is it irreducible? Can you get from every state to every other state with some positive probability? Yeah, sure. You can get from 0 to 2 easily. And you get from there to 1. So 0 leads to everywhere else. From 1, you can get to everywhere else as well. And from 2, you can go anywhere you want. So yes, this is irreducible. Okay, so what does it mean? Well, show that it's irreducible. Well, I did by just realizing that I can get from any state to any other state. I don't think I would do more than what I just said. It's pretty clear from the diagram that you can get with positive probability from any state to any other state. you wanted an example, you could say, suppose you want to get from 0 to 1 in some length of time. One way to do it would be to go from 0 to 2 and then from 2 to 1. The probability of that would already be, that particular path would be 1 times a half. So this would be bigger than 1/2. So I think it's pretty clear it's irreducible. Let's go to B, find the period. Oh, the period's not so obvious. If there were a loop, the period would be 1 and I don't have to do anything. The fact that it's irreducible, there's a result that says in an irreducible Markov chain, the period of one of them is the same as the period of any of them. So let's just find the period of 0. Period of 0 by definition is the GCD. This is the stuff we did in class earlier of all n, such that in n steps you're going from 0 to 0, right, with positive probability. So look at all ways to go from 0 back to itself in n steps. Can't do it in one step. There's no loop. So 1 isn't in here. Can't do it in 2 steps. Well, I guess it can. It can go 1 and then here. So there's a way to get from 0 back to itself in 2 steps. Go up from 0 to 2 and then 2 back to 1. So 2 is in here. Okay. What about 3? Can I do it in 3 steps? Sure. I can go from here to here, here to here, and then here to here, and I've gone from 0 back to itself in 3 steps. So 3 is in here. I don't need to go any further. Why? I'm looking for the greatest common divisor of 2 and 3. 2 divides this, but not this. 3 divides this, but not that. The only thing that's an integer that divides both of them is 1. And that doesn't matter what else is in here, because 1 divides everything. So I'm saying this is already 1. The argument is this. This thing is asking me to take the greatest common divisor of a whole bunch of numbers. But if I just look at the greatest common divisor of the first 2, that already assures me that the greatest common divisor would have to be 1. I need a whole number that divides 2 and 3 evenly. And the only whole number that does that is 1. Whole positive number, by the way. And 1 would divide whatever else is on the list anyway. So the GCD of this is 1. So the period is 1. So what is this thing? So I know D0 is 1 by a theorem that also tells me D1 and D2 are also 1, which tells me this whole chain is what? Aperiodic, which is what I need by theorem 7 to imply what? This thing is a steady state. Oh, well, it has a steady state distribution. Now let's see what they wanted me to prove. Well, I just proved it's aperiodic, and that's all they wanted at this stage. That was part. Well, I showed that it's aperiodic. Now they want the stationary distribution. Okay, to find the stationary distribution, it's a 3-state guy. So probably the easiest way to do it is just do it by hand, unless you have that algorithm in front of you or something.
Wait, Professor,
Yeah,
just to double check, so if it's periodic, then the D's would all equal to a different number?
that's correct.
Okay.
Yeah, so if it was periodic, then the D's would all still be the same if it's irreducible, but it would be something other than 1. It's some constant period other than 1 if it's periodic. If it's aperiodic, then all the D's would be 1. Okay, so let's solve this, I guess, to finish the problem. So we need all we need to do is solve this equation. And in this case, it's P0, pi0, pi1, pi2. Pi0, pi1, pi 2 times p. And p I've already forgotten, but it's up there. 0, 0, 1, 1, 0, 0. 0, 0, 1, 1, 0, 0. Then what was the last row? 1 half, 1 half, 0. Okay. 1 half, 1 half, 0. Okay. So if I multiply, well, let's get the equations. Pi 0, first entry on this side, would be what you get when you multiply this row vector times this column vector. This times this is 0, but then you get a pi 1. And then you get 1 half pi 2, right? So the first equation is giving me this. Second equation would be giving me pi 1. And when I multiply this row vector times this column vector, I just get pi 2 times a half. Okay. And then finally, the last equation, pi 2 would be equal to this row vector times this column vector, which would just be pi 0. So that gives me pi 2 equals, what did I just say? Pi 0, is that right? Everyone see where I'm getting my three equations? Just by doing the indicated matrix multiplication. But I'm feeling pretty happy about it because this is telling me pi 2 and pi 0 are the same. So that's helpful. And if I put that into here, that tells me what pi 1 is. Pi 1 would be pi 0 over 2. So now I can picture what the pi vector could be. It's not a hard system to solve. It would have pi 0 this, and then pi 1 would be pi 0 over 2. And then pi 2 would just be pi 0. So it looks like this, just making use of what? These two equations so far. I knew that the first and the last components were the same, and I just replaced it all in terms of pi 0. And then pi 1 was just pi 2 over 2, but that's the same as pi 0 over 2. So I have this all being it. But then I also remember that this is a distribution, so that pi 0 plus pi 0 over 2 plus pi 0 should all equal what? 1. So what is that? That's like 2.5, which is 5 halves. Pi 0 equals 1, so that implies what? Pi 0 is 2/5. So this is 2/5, and this is 2/5. And this would be that divided by 2, which would be 1/5, and it looks fine. Okay, so I think we found the stationary distribution. If we really wanted to, we could put it back in here and check. But I'm pretty sure I did it right, so I'm not going to even check. It wouldn't take long to check. It's probably a good thing to do. Okay, so it's a good thing to do. I probably should model it. Okay, so all right, so put in what? 2/5. What do I have in there? If I could read my own writing, I'd be okay. Pi 0 is 2/5, so 2/5, 2/5, and this is 1/5. Okay, so when I multiply this by this, I'm going to end up with 1/5 plus another 5th, which should be 2/5, and that's correct. And when I multiply this times this, I'm just going to end up with pi 2, which is 2/5 over 1, which is just 1/5, and that's what this is. So these two check. 1/5 is here. And then finally, this times this just gets me 2/5, and that's what's here. Okay, so I've checked it, it works. Now, as far as the problem is concerned, we're done. We found the stationary distribution. But my additional question is this the steady state distribution? The answer is yes. Why? Because the chain is aperiodic. We already checked that. And we have the unique stationary distribution. So by theorem 7, this stationary distribution is also the steady state distribution. Okay. Now, by the way, if you wanted to take powers of this thing, then you could check and see as you went along that you wouldn't have that oscillating behavior that we had in class before. Everything would be approaching the same thing. But I didn't ask you to do that. All I asked you to do is verify this is the steady state. And you do that by first finding the stationary, which I've done, and then also realizing it's aperiodic. So theorem 7 tells you that this solution here, the 2/5, 1/5, 2/5 is the steady state. What does that mean? As long as time goes by, there's a 40% chance of being here, a 40% chance of being here, and only a 20% chance of being in the middle. Because those are the percentages you get from this. Questions,
Oh, I have a question.
please?
I was wondering, like for part A, I stepped out for a second, I was wondering how we got that.
How did we get that it's irreducible? Is that what you're asking?
Yeah, like the part is like P to the N and then the 0, 1.
Oh, you mean this part here?
Whereas like less than 1/2, which is a little down.
Middle down. Oh, this part. I don't know what I was doing. Let me see what I'm doing there. Oh, I'm looking. Let me think about what I was doing. Hang on a second. So this I had from the class that gave me the stationary distribution. I think I was just trying to show that the GC, that it was aperiodic. But I'm looking at this and trying to recognize what's going on. I'm not remembering why I wrote this, if that's the part you're asking. Let me think about it another minute. P to the N 0, 1 greater than 1/2. I don't remember what I was doing when I wrote this down or why I wrote it. But I think I was, oh, I do remember now. I was trying to argue it was irreducible. So irreducible means if you start at any state, there's a positive probability of getting anywhere else. And that's what I was saying here. So if I started at 0 and I wanted to get to 1, I could see that if I go up this way and then down this way, that will get me from 0 to 1 in 2 steps, right? And so then the probability of doing that was 1 times 1/2, which was this. So this is one way to get from 0 to 1 in a positive number of steps. And all I'm really trying to argue is that there's a positive probability of getting from any state here to any other state. And I just gave 0, 1 as an example. So maybe that's what you missed.
Yeah,
But-
that sounds good.
Yeah, and that's basically all. And I was just saying the same thing holds in general. It's pretty clear that you can get from any state here to any other state with positive probability. And that's all the irreducibility means. So that's sort of old stuff. The newer stuff was this part. Are you okay on the newer stuff, the aperiodicity? Maybe you came in on that part.
Yeah, I was here for that. I got that part.
Okay, then we're good. Anyone else have a question? Okay, so we've done 2 problems. I can look at 15. That was the next, no, which one? This 23. Though it's virtually the same as this one, except you got more states to deal with. So finding the stationary distribution will be a little more challenging. Maybe you'll want to use the algorithm, or maybe not. I don't know. The matrix doesn't look too bad. But then when you're done, you have to do the aperiodicity, check to find the periodicity of the states. And if they're 1, then it's the steady state. So I asked you to follow up and check and see if there's a steady state distribution. So if you want me to do that, I could do that next, or I can go back and talk about the problem that I haven't talked about at all, which was what? 15, I think, which is, I think, a little different. Or I can go in another direction entirely. It's up to you. So anyway, I'll go whatever people want. If we do 23, I'll probably bring you into the game, asking you to help me with the stationary, or I'll do it by hand, one of the two. I don't think I'll use the algorithm. Maybe I should, but we probably could do it together. Anyway, what do you want to see? Any request? Well, I don't know. I'm happy to do one, even though no one's requesting it. I'm trying to figure out what's the best one to do. Is there anyone who wants to give me a direction? So I'm thinking of doing either 23 or 15 between those two.
I think 15, since the computation doesn't seem so bad, but I'm not sure. I'm leaning towards 15.
15 is a different idea. So maybe your request makes sense, Millie, because 23 or whatever, let's see what I just did. Yeah, 23 should follow along the lines of what I just did. It'll just be more complicated because it has more states. So why don't we look at 15 at least? Because that's newer, and that may confuse you more. Maybe. Let me flip the page. Add a new page. Okay, let's see what 15 is about. I think I chose 15 just because it's a problem that you probably should see, not one that's particularly related to the lecture. So the transition probability of a Markov chain is called doubly stochastic. Yeah, that's a new idea. If the sum over X in the state space is equal to 1. What is the stationary distribution of an irreducible Markov chain having D less than an infinite number of states and a doubly stochastic transition function? Okay, so let me tell you what they're doing here. Let's just do it for 2 states. So consider the 2-state Markov chain. Okay, we've done that a lot. So that looks like this. And we usually use P for going up and Q for going down. And then this becomes what? 1 minus P. And this becomes 1 minus Q. Okay, then what is the transition matrix. From 0, you can go back with 1 minus p probability, or you can go up with p. And from 1, you can go down with q, or 1 minus q, you can loop. Okay, we already know that this is the one-step transition probability matrix. So we already know that the rows add up to 1, and that's pretty clear by the way we've symbolized these in terms of probability. 1 minus p plus p, the p's cancel, and the first row adds up to 1. Q plus 1 minus q, the q's cancel, and the second row adds up to 1. And all I'm saying is what we've already said before, p is stochastic. Stochastic means what? The rows add up to 1. Okay, that's true for any one-step transition probability matrix, no matter if there's 2 states, 3 states, n states, or even an infinite number of states. The Markov chains we've studied always have the rows adding up to 1. Now they're bringing in a new idea. Suppose the columns also add up to 1. If the columns of P also add up to 1, the P matrix is called doubly stochastic. Or if you prefer, the chain is called doubly stochastic, or the Markov chain is doubly stochastic. And if you haven't figured out yet why the word doubly is there, because we already know the rows add up to 1, because that's what stochastic means. But we're adding a new condition that the columns also add up to 1. And that's not been required before. If it happens, that's sort of like a bonus or icing on the cake. And the question is, if that happens, what is the stationary distribution? So why don't we try it in the 2x2 case to get some intuition, okay? It's not letting me go down, so let me see if I can fake it into letting me go down. Okay, it's not as much as I'd like, but it's better than nothing. Can I get a little more? It's begrudging me, but it's giving me, I don't know how this thing is working, clearly. Okay, so suppose this is doubly stochastic. Oh, by the way, do we already know the stationary distribution for a 2x2? Hopefully. The stationary distribution for the 2x2 case is Q over P plus Q, and what? P over P plus Q? Okay, we've dealt with that before. I don't know, how many of you have that in your mind? If you don't, then you need to redo it. Well, let me see. So I'm going to make that less of a rhetorical question and make sure people know. So Ricky, I see you know it. That's good. How many people know that that's the stationary distribution for the 2x2 case? So again, Ricky, do what you did before. If you will, give me a thumbs up or hands up or something. Gotcha. Millie knows it. But the others aren't saying they know it at all. So, okay, it's it's something you should know. So let me just take the moment to verify it, and then we'll go on. So where am I? I'm over here. Reshare. Wonderful. Now it won't let me go even below. Oh, come on. Wow. Oh. Yes, yes. Okay, I'm coaxing this thing into giving me more room, so I don't have to move to another tab. There, perfect, thank you. Okay. So why is it true? Okay, so for the 2x2 case, if you just take P, well, I'm sorry, go back to the 2x2 case, which is 1 minus P. This won't take, oh goodness. 1 minus P and P, and this is Q and 1 minus Q. And if you multiply that pi 0, pi 1, and you set it equal to pi 0, pi 1, then pi 0 would be the first row times the first column. So that would be pi 0, 1 minus P, plus pi 1, Q. And I'm not even going to write the second one because I don't think that will look pretty much like the first one. But from this one, what can we write? We can write, this is, so pi 0 is pi 0 times 1 is just that, minus pi 0 times P, plus pi 1 Q. So just multiplying through, this cancels this. And remember that pi 0 plus pi 1 is 1. So if we kick out, so what does that mean? Pi 1 is 1 minus pi 0. So if we put that in here, we would have 0 equal to minus pi 0 P plus pi 1, but pi 1 is 1 minus pi 0 Q. And this should be enough to solve for pi 0. So what do we get? Pardon me. You get minus pi 0 P minus pi 0 Q. So you could factor out the minus pi 0 if you want. And that's the P plus Q. And then there's plus a Q from here. And from here, you can solve for pi 0. And it would turn out that pi 0 is Q plus Q. And then since it has to add up to 1, pi 1 would be P over P plus Q. That's not all adds up. Okay, so that's the quick verification that for the 2x2 case, this is the stationary distribution. Now let's add the additional condition. The additional condition is it's doubly stochastic, which means when I add the rows together, we also get 1. So let's add that into this. So the first row also adds up to 1. So that's 1 minus P plus Q. Usually this doesn't hold, but this is an additional condition we're adding. So the first column adds up to 1. The ones can be canceled, and this means Q equals P. But if Q equals P, and we already know, well, What does that mean? If Q equals P, then both of these are half, right? Because both of these are the same. And they both add up to 1. So that would imply that the stationary distribution now would become 1/2, 1/2. You see why? Because if the first column adds up to 1, then P and Q are the same. If P and Q are the same, the stationary distribution are the same fractions because the numerators are already the same. I'm sorry, the denominators are already the same and the numerators are now the same because of this. So they don't both have to be 1/2. So in the 2x2 case, if we add the condition that the matrix is doubly stochastic, what happens? It turns out the distribution no longer looks like this, but actually specializes down to this, which is uniform. They both have the same probability, right? That's a uniform probability. Okay, so that happens in the 2x2 case. And now what are they asking us to do? They're asking us in 15, what is the stationary distribution of a Markov chain having D, finite number of states, and doubly stochastic transition function or matrix? Okay. So what would be your guess in the 3x3 case? Do you have a guess? If I had 3 states and the matrix was no longer just, like this, but there were arrows flying all over between the 3 states. And in addition to the matrix being stochastic, it was doubly stochastic, which means the rows would also add up to 1. Do you have a guess what the stationary distribution would look like based on what we just did? Evidently not. Okay. Now let me tweak that a little. Let me see if I can get a response a little further. We just did the 2x2. And doubly stochastic meant the probabilities of the stationary were the same. What would you think is possible for the 3x3?
1/3. I don't know.
Yeah. Why not? Why not be, optimistic? Or in this case, doubly stochastic meant the stationary. There were a lot of stationary distributions, but the doubly stochastic ended up selecting the uniform one, where they were both the same. So if it's a 3x3, I'm suggesting if you took a leap of faith, maybe a third, right? Okay. Okay, do you first understand the idea of where that's coming from? It's coming from the 2x2 case that we just actually solved for it. So the suggestion is maybe for the 3x3, it should be a third. Now, do we want to try to solve it again the way we just did it for the 2x2? Not if we can avoid it. If we can avoid it, then I'd rather not go through this whole solution process. Why? It wasn't painful. It was only a 2x2 case. And the double stochastic condition just meant this, that meant P and Q were the same. But I probably would prefer not to do this again. I would just like to test our theory. So can we just test it? Why not? Let's test the theory. So suppose you had a 3x3 guy. Well, that's a lot more a lot more entries. Let's put in some matrix kind of notation. 0, 0, 0, 1. Oh, we have the notation, but I'm not doing it justice. We've already written this way. This would be 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. This is familiar notation from, listing out the entries of a 3x3 matrix. 2, 0, 2, 1, 2, 2. Excuse me. I think talking is going to get me to cough, which is to say my cold is getting worse. That's okay, because I think it has to get worse before it gets better. All right, so let's suppose this is our 3x3 matrix. Now, let's see, what else did they say? Irreducible. Okay, so that means every state has to be able to get to every other state. And what else? Markov chain, okay. but also doubly stochastic. So what do we know? Now we'll assume both. The rows sum up to 1, and the columns sum to 1. So if I add these 3, I get 1. If I add these 3, I get 1. I get these 3, but I get 1. That's the definition of doubly stochastic, okay? So that's what we get to assume. We're assuming that the rows and the columns add up to 1, and that the other thing we get to assume is what? It's irreducible. Okay. So from having done the 2x2 case, we're thinking, oh, by the way, when you make a guess in math, if it's an educated guess, you call it a conjecture. What is our conjecture? 1/3, 1/3, 1/3. That's our conjecture. We're not sure, but we're trying to see if that may work, because that's what happened in 2x2. Oh, by the way, do we know anything else? Yeah, we know theorem 5 from class. If you have an irreducible Markov chain, and the states are positive recurrent, and they will be because there's only 3 of them here. So you can't have any null recurrent states for a finite chain. So we know by theorem 5 there's only one solution, right? That's theorem 5 says there's only one solution of an irreducible Markov chain having positive recurrent states. So theorem 5 says there's one solution. Our guess is this is it. So let's test it. How do you test it? Well, if this is a stationary distribution, it has to do this, right? Why? That's the definition of being a stationary distribution. It has to have 2 properties. It has to satisfy this condition, and it has to be, a distribution. It has to add up to 1. Okay, so put it in. 1/3, 1/3, 1/3. Up against what? B0, 0, B0, 1, B0, 2, B1, 0, B1, 1, B1, 2, B2, 0, P21, P22. Okay. So let's just do this and see if it comes out to be 1/3, 1/3, 1/3. Some blanks to fill in here. So if we multiply this times the third and this, we do a really like it's a dot product, this row vector dotted with this column vector. But when you do that, what are you going to get? You're going to get 1/3 P00 plus 1/3 P10 plus 1/3 what? P20? Because that's what happens when you just multiply this row vector by the column vector. But you can factor out the 1/3. And that's P00 plus P10 is P20. But that's the sum of the first column. And what did we assume about the sum of the first column? We assumed it was 1, right? It's up there, column sum to 1. So this is 1/3 times 1, which is just 1/3. So this guy's a third. So it's looking good. Why? Because we're trying to verify whether this is the stationary distribution. So when you multiply our conjecture by P, do you get the pi coming out? Well, let's just check the other one. The other one would be 1/3, 1/3, 1/3 times this thing. But that would look almost virtually the same as this. We could factor out the thirds. And the second row sums to 1, so it's going to work again. And this times the last column, each of these things will be multiplied by a third, factor out the third. The sum of this column is 1 by assumption. Cool. Done. Almost. Does everyone see that it works? I did the first one more carefully. I did this times this column and showed you how the 1/3 factors out, and then you get the sum of the first column, but that's 1 because of the doubly stochastic assumption. 1/3 times 1 is a third, so that's this. The same argument works for multiplying this row vector times the second column or this row vector by the third column. And again, you're using the fact that it's going to work out because the sum of each of these are 1. So we've now verified for the 3x3 case that if it's doubly stochastic, that the uniform probability, 1/3, 1/3, 1/3, is the stationary distribution. Questions so far? Cool. So the cool is done. And the done is done. And what's the almost? Well, we only did it for 3x3, right? How about I leave the rest to you? Now, if you're not sure what to do, I can tell you, we'll do a 4x4. And check it with what? 1/4, 1/4, 1/4, 1/4. So that's if you don't know what to do. But if you do know what to do, you're not just satisfied with the 4x4 case. You want to go to the n/n case, right? Because we're trying to show what it would be in general. We're not just trying to do it for the 2x2. 2x2 is 1/2, 1/2. 3x3 is 1/3, 1/3, 1/3. We're trying to show that in the general doubly stochastic case, the stationary distribution is equal to 1/n, that it's uniform. So that would be the next case I would suggest doing. That's the general case. What's the good news? It should work in a similar manner. Questions? It's cool. Why is it cool? Because the uniform density is the nicest probably thing you could hope for. It's saying that, well, what is it saying? If this could be the steady state, right? If it were the steady state, it would be saying that after a long period of time, there's a third chance that you'll be at each of the states. Which means if you assume something's doubly stochastic, that has the nice consequence of being equally likely to be at any of the states when it's running a long time. Which is a nice payback for that assumption. Let me see. Oh, question. Suppose we do all that. Suppose we show it's 1 over n. Is it automatically the steady state distribution as well? So that's a tagline. That's a question to worry about after you do it all. Stationary is cool, but steady state is even better because that's intuitively telling us long-term behavior. And my question is the long-term behavior 1 over n, is that the steady state behavior? Anyone have an idea? Yes, no, maybe? Let me help you. If somebody says a chain has a stationary distribution and it's unique and it's on an irreducible chain, what more condition do you need to have in order to nail it down to be the steady state distribution? You need a little more. And we talked about in class today. What more do you need?
The A something. The
Yeah.
word.
Yeah, okay. You got, at least you got the idea. Thank you. You need aperiodicity. It's a complicated, it's a multi-syllable word. You need it to be aperiodic. Which means, there are many ways that could happen, but you need that added condition. Why? Because we already had one earlier today. I'm thinking we had one. I'm trying to remember it. Let me see if I can just cook it up. Is this going to let me go below? I got to play games again. All right, I'll play. What about this guy? So this is going back to what we did earlier today. What did we just, we're going up and down, but no loops. So let me see how this would work. There's no loops. This would have to be a half if I want it to work. I guess this would have to be 1. Yeah, with no loops, it looks like this, right? Okay. It's irreducible, right? You can get from any state to any other state. So that means there's a unique stationary distribution. Could we actually figure out what it is? Maybe, and we should be able to. What does P look like here? 0, 1, 0. I think we did this in class today, or something like it at least. This is 1/2, 0, and what? 1/2. And the 2, 2, you can't get to 0, you have to go to 1, and you can't get here. Okay. Okay. So this is the kind of thing I think we did today. And when we took powers of it, it was an alternating thing, right? Wasn't it alternating between 0 and a half? I think we did almost the same example. Which means what? Well, first of all, okay. Well, this is interesting. This is an example that this thing does not have a steady state because it was alternating. Okay, and that's what we did earlier today. However, this thing is not doubly stochastic because the rows don't add up to 1. So is it possible to have, if it's doubly stochastic, I think this has to add up to 1. And so does this, and so does that. What does that mean? I think that means well, here's the question. If it's doubly stochastic, does that mean we have a loop? If we have a loop, then it's aperiodic and we're done. So maybe this thing is 0. So it doesn't have a loop at 0. And if this were 0 and if this were 0, then it would have no loops at all like this. But then these two would have to add up to 1 and these two would have to add up to 1. I'm trying to see if you actually could have, can you actually have something that's doubly stochastic that doesn't add up to 1? Well, no, it has to add up to 1, but that doesn't have a loop. So let me see if we can create something like that. So maybe something that looks like, I'm just trying to create that. Maybe it's 0 here and a half here and here. And then maybe 0 here and a half here and here. And maybe 0 here and a half here and here. Is that doubly stochastic? Yeah. The rows add up to 1, the columns add up to 1. Okay, so that's doubly stochastic. How does it actually look? Well, it is this. But it has no loops. So if I were to draw it, it would look like this. Half probability of going here. Half probability of going here. Half probability of going back this way. Half probability of going this way. And then half probability of going down there. I need more room. Come on. Thank you. Half probability of going this way. And the half probability of going this way. Wow. I think I messed up. Let me see. Half going from here to here and here to here. That part's fine. Half going this way and half going that way. Usually we don't draw those arrows looking like that. So let's draw that differently. So this is going down and this is going up. And then this one would be going down twice this way and this way. Okay. So that's what we have now. It's doubly stochastic. Is it periodic or aperiodic? It has no loops, but it still might be aperiodic. Let's check it out. Let's find out what the period is at 0. So the period at 0, by what we did today, is the GCD of all n greater than or equal to 1, such that what? You can get back from 0 to 0 in n steps with some positive probability, right? Okay. You can't get back from 0 to 0 in 1 step, so 1 is not in here. But you can do it in 2, right? You can go up and then you can go back. So 2 is in here. 1 is not. How about 3? You can go up, up, and down and go. 3's in there. Don't have to go any further. The GCD of these is 1. Okay, so this is an example of something that is what? Doubly stochastic, aperiodic, so it will have a steady state. And the steady state, from what we just proved, will be 1/3, 1/3, 1/3, as we did the 3x3 case. Now, what I'm trying to find is it true? Is it true that every 3x3 matrix that's doubly stochastic will be aperiodic? I mean, here's one that is doubly stochastic and it is aperiodic. Is it possible that there's something there that's not aperiodic? If that's the case, then it won't have a steady state, right? If it's not aperiodic or if it's periodic. I don't actually know the answer to that question offhand. So I think what we've answered the question 15. The question of 15 is what's the stationary distribution of a doubly stochastic Markov chain? And the answer is the uniform distribution, using the stuff that we just did above. Using the same idea of this of 1/3, just do it for 1/n. So that answers the question of 15. But what we've done is gone beyond that. This is how research is done, by the way. You get one result that the problem is asking, and then you ask, what about in general? So what I'm asking in general now is, does every doubly stochastic Markov chain have a steady state, a unique steady state? I know it has a unique stationary, but I don't know that unique stationary is always aperiodic. If it is, theorem 7 gives us the result. And that would be a nice result. It would say that every doubly stochastic Markov chain has a steady state distribution, which means it would have long-term probabilities. I don't remember doing that in the past. Maybe I did. I just don't remember it right now. I tried to cook up a counterexample. This is doubly stochastic. If this were aperiodic, if this were periodic, then you'd have an example of a doubly stochastic chain that doesn't have a steady state. But it turned out this thing is aperiodic, so this thing does have a steady state. So I don't know. I don't know the answer to my own question. You can try to cook up something. I think if you're going to try to find something, I know you got to avoid the loops. So I think I'm almost playing with this more than I should, but it's curiosity to me. We're assuming there's no loops. If there's no loops, could it still be periodic? I think if you have numbers here. Yeah, even no matter what, let's see, how did we get the 2 and the 3 is the real question. The 2 and the 3 came from going from 0. That was this thing. So you could get back in 2 steps, and you could also get back in 3 steps. I think it's true, but that's only intuition. I don't know. Anyway, I'm well past what the homework is. I'm just getting off on something. Any questions? I think we should quit. Or I should probably quit and get ready for my next class. But it is an interesting question. I don't know the answer to it. I'll think about it. If you want to think about it too, do so. It'd be even cooler if you figured it out. That'd be cool. All right, I'm out. See you next time.
Thank you.
Yeah, thanks.
Thank you, Professor. Hope you feel better.
Yeah, I think it's got to run its course, but I've been there before. Thank you much.
See you Wednesday.
But take care. Bye.